A study was done in which subjects who had suffered from a stroke were given either placebo or aspirin. 3 years later, it was found that 33 of the 685 subjects taking placebo and 18 of the 678 subjects taking aspirin had a heart attack. We want to first report the data in the form of a 2x2 contingency table. So 33 of the placebo and 18 of the aspirin takers both had heart attacks, out of 685 and 678 respectively. For the no column here, we would have 685 minus 33 to get 652, and 678 minus 18 to get 660. This column adds to 1,312, and this column adds to 51. So now we want to first carry all of our given steps of the null hypothesis that having a heart attack is independent of whether one takes placebo or aspirin. Alright, so to carry out all those steps. So the first thing that we need is that we first need two categorical variables. Randomization was used to obtain the data, and that the expected counts are always 5 in all cells. Which, if we type all of our data into the template I have here on the right, I'll just very quickly do that and get rid of this last column. So make it kind of bigger to see. There we go. It's a 2x2 table. We have down here, each of these expected counts are all above 5. So those are good. Likewise, from this we can give our null and alternative hypotheses. So for the null hypothesis, this would be taking aspirin and having a heart attack are independent for this chi-square test. Likewise, the alternative hypothesis is that taking aspirin and having a heart attack are dependent. Okay? And we can run this hypothesis test, whoopsie-daisy. We can run this hypothesis test in this template I have here to the right. Again, let me just make that a tiny bit bigger. We could see that we have a chi-squared test statistic here of 4.42. Since we want to run this to 3 decimals, though, let me expand this out a little bit. So 4.425. So the chi-squared test statistic is 4.425, and likewise the p-value we're given here is 0.0354. To round that to 4 decimal points. Alright. So now based upon this we could write out our conclusion of this chi-square test. Here we are rejecting the null hypothesis and conclude that the two variables are dependent or associated. Now for question number 11. We have test scores for a history class had a mean of 79 and a standard deviation of 4.5. Test scores for a physics class had a mean of 69 and a standard deviation of 3.7. We have suppose a student gets a 68 on the history test and an 87 on the physics test. We want to calculate a z-score for each test, and then on which test did the student perform better. Z-scores. The formula for those are that we take the mean, we take the value of the variable, subtract the mean, and then divide by the standard deviation. So let's do the history first. We were given that the history class has a mean of 79 and a standard deviation of 4.5. And that the student got a 68 on the test. So the calculation for that 68 minus 79 divided by 4.5, round into 2 decimals, this gives us a negative 2.44 for the z-score. For the physics test, we were told that the test scores have a mean of 69 and a standard deviation of 3.7. And that this student got an 87 on it. It's pretty good. Round into 2 decimal points, this gives us 4.86. So which one did the student perform better in? The physics z-score is a lot higher, so physics. For question number 12. And let me just quickly move this on over a little bit so we could see more of this table. And I need a new template for this. We have here, as I go to make this bigger, we have that the summary statistics in the table are for a comparison of females and males on the number of hours a day that the subject watched TV. And that's this table here. We want to set up the hypotheses of a significance test to analyze whether the population means differ for females and males, and what the correct hypotheses for this test. The null hypothesis, since we have ourselves two means, are that the two means are equal. And here I'm letting the females be group 1 and males be group 2. Likewise, we want to see if the population means differ for females and males. So the alternative would be a two-tail hypothesis test. Mean 1 does not equal mean 2. Okay? So then, based upon that, for part B, we want to use software which you can use summarized data like I have here on the right in my Excel template that kind of decided to not display as nicely as I would have liked. But that's alright. We'll get it eventually. But from this, though, we want to conduct all parts of the significance test and interpret the p-value and report the conclusion for a significance level of 5%. So based upon this, to conduct all those parts, we need to do a couple of things. So we first need to put our data into this template. So actually, I probably should have left that a bit further out. Okay, so we were told in here that we had, for females first, the sample mean was 3.06. standard deviation was 2.59, and the sample size was 671. For males, this was 2.67, 2.45, and 639, respectively, for sample mean, sample standard deviation, and number of data points. Oh, and I need to sort this summary statistics box for this. And we want our alternative hypothesis, being that these are not equal. We need our test statistic, which we are given on here to be 2.80. Okay, so our test statistic is 2.80. And you know what, let me actually type this out so it's a bit easier. Test statistic is 2.80. The p-value, which we could find on this template if I bump this over, the p-value is, for this test, going to be 0.005. 0.005. So now, based upon this, since the p-value is less, much less, very less, that was not correct, very less than 5% or 0.05, we are going to reject the null hypothesis. Conclude that the mean number of hours a day females watched TV is different from the mean number of hours a day males watched TV. And then if you were to construct a 95% confidence interval comparing the means, would it contain 0? And we want to answer based upon the results that we just found in part B, without actually finding that interval. Mind you, we could see that interval in here of 0.12 to 0.66, which does not contain 0. But that's, that's besides the point. So for this, we give, since the test provides sufficient evidence to reject the null hypothesis, 0 is not a plausible value for the difference between the population means. So a 95% confidence interval comparing the means would not contain 0 based upon this test that we just found.